In this video, I'm going to be working through the sample problem that is on slide number 8 of your chapter 9 notes. Okay, so in this problem, we're using the same balanced equation that we used in our problem on slide number 7. So that's where this comes from. You don't need to rebalance it. All of the examples in your PowerPoint are using the same balanced chemical equation. Okay, so now we're being asked to answer a different question. Okay, so this question reads, what mass of carbon dioxide, okay, so we want to know information about carbon dioxide, will be produced when 44.1 grams of propane react. Okay, so we're taking 44.1 grams of propane. Okay, that's the same number that we had in number 7. So we have 44.1 grams of propane, and we want to know how much carbon dioxide mass, so that's going to be grams, right? What mass in grams are we going to be able to produce, okay, if all of that propane reacts? So we're given a mass of propane and we want to find a mass of carbon dioxide. Okay, so what I want us to do is I want us to take a look at our flow chart and kind of figure out where we're at and where we want to go with this problem. Okay, so we're starting off with one substance. In this case, we're going to call substance A propane, right? We're starting off with the mass of propane. So we're down here in the bottom left of our flow chart. We're given the mass of one compound, and we're asked to find the mass, right? Mass in grams of a different compound. So that's mass of a different compound, okay? This setup is going to be very similar to what we did in number 7. However, instead of wanting to know the mass of oxygen that it would need to react with, we want to know what's the mass of carbon dioxide that will be produced here. Okay, so we're going to go one step at a time. Okay, we're going from this part of our flow chart to this part of our flow chart. So we're going to need to go 1 step, 2 steps, 3 steps. Okay, so in our first step, we're going to go from mass of A, which is our known compound, which we said was propane here, right? We know the mass of propane. So we're going to go mass of propane to moles of propane. Okay, and in order to do that, we're going to need the molar mass of propane. Okay, remember, we calculated the molar mass of propane in number 7. Okay, so if you wanted to start our T-chart, okay, the first conversion factor needs to be going from mass of propane to moles of propane using that molar mass. So that's what we're starting with, right? And we said that first conversion factor is going to be the molar mass. Well, we found in number 7 that 1 mole of propane weighs 44.09 grams. Okay, and just like the previous problem that we did in the last video, you'll notice, I'm not just writing grams and moles, I'm writing grams of propane, moles of propane, grams of propane, right? We want to be very specific when it comes to which compound we're dealing with, because, once again, we're going to be converting between 2 different compounds. We can relate their moles from our balanced equation. Okay, so make sure you're labeling everything beautifully. Okay, so that was our first step, right? We wanted to go from mass to moles. Well, if we stop this problem right here, we've canceled out our mass of propane. We would be at moles of propane, moles of A. But we don't want moles of propane. We have to get all the way down here. Okay, so our first step is done. Now we're at moles of propane. We can go from moles of propane to moles of oxygen. Okay, and again, this is the only thing that's new here. Okay, and all we're doing is we're taking this balanced equation and we're saying, what is that relationship? Every 1 propanes gives me 3 carbon dioxides, right? If I put in 1 molecule of propane, I will get 3 molecules of carbon dioxide. Okay, well, what if, reacting 1 molecule is not really possible? So what if I put in 1 mole, or 6.022 times 10 to the 23rd molecules? Okay, 1 mole of propane. Well, it would give me 3 times as many moles of carbon dioxide, right? So that relationship there, our mole ratio in this problem, our mole ratio is that every 1 mole of propane that reacts is going to give us 3 moles of carbon dioxide. Every one we input is going to give 3 out. Okay? So we know when we're going from moles of propane, which is where we're at, to moles of carbon dioxide, we need to use that mole ratio. Okay, and anytime you have an equivalence like this, you can turn it into a conversion factor. You just need to make sure you know which half goes on the bottom and which half goes on the top of that conversion factor. Okay, right now we are at moles of propane. We want to get rid of moles of propane, so we need to put 1 mole of propane on the bottom of our column in our T-chart. Okay, and again, these values here are coming from my balanced equation. Okay, every 1 mole of propane that reacts is going to spit out or give me 3 moles of carbon dioxide. Okay, so we just did this step, and I apologize, I'm kind of squished for room here. We just did this step where we went from moles of propane to moles of carbon dioxide. Okay, so when we did that, right, we canceled out moles of propane. If we stop this problem right here, we would be at moles of carbon dioxide, right? That's the only unit left in our T-chart. But of course, you know, we don't want moles of carbon dioxide. The question says what mass of carbon dioxide. So we have one final step here. Okay, we need to go from moles of carbon dioxide to mass of carbon dioxide. Okay, and the way we're going to do that is through the molar mass of carbon dioxide. Okay, this is the molar mass of compound B here. Okay, so we need to figure that out real quick because we didn't do that in number 7. What is the molar mass of carbon dioxide? Well, you have 1 carbon, and carbon's molar mass is 12.01, and you have 2 oxygens, and oxygen's molar mass is 16. Okay, so when you put this in your calculator, you're going to end up with 44.01 grams per mole. Okay, and again, what this means is that in 1 mole of carbon dioxide, you're going to have 44.01 grams. Okay, so that's our molar mass that we want to use to go from moles of carbon dioxide to mass of carbon dioxide. Make another column in your T-chart because we're doing another conversion step. Okay, we know that 1 mole of carbon dioxide, grams per 1 mole. Okay, I'm putting moles of carbon dioxide on the bottom so that they cancel out. We know that that 1 mole of CO2 is going to weigh 44.01 grams. And again, look at, I'm labeling everything carbon dioxide, carbon dioxide. Okay, just like here, I canceled out grams of propane. This grams now, this is grams of carbon dioxide. Okay, so make sure you're labeling really, really well so you know what the heck you're doing. Okay, so we, in that 3rd step, cancel out moles of carbon dioxide. Okay, do a double check. Make sure all of your units cancel. Grams of propane, moles of propane, moles of propane, moles of carbon dioxide, moles of carbon dioxide. The only unit left is grams of carbon dioxide, okay, and that's what we're looking for. Okay, so once you have your T-chart set up, math is pretty straightforward. Again, everything on the top is going to get multiplied. Everything on the bottom gets divided. Okay, so we've got 44.1 divided by 44.09 times 3 times 44.01. Okay, we get this number. We need to think finally about rounding. Okay, well, our problem gave us 3 sig figs. Okay, this is an exact relationship. This is not sig figs. This has infinite sig figs. Excuse me. Okay, so we want to round our answer to 3 significant figures. Keep. Final answer, 132 grams of carbon dioxide. Okay, let's do one more. Let's look at the problem on slide number 9. Okay, so our question on slide number 9, again, we're referencing the same balanced equation that we just used for 7 and 8. Okay, this question says, how many particles of carbon dioxide will be produced when 3.89 times 10 to the 23rd molecules, of propane react? Okay, so what do we know? What's our compound that we know about? And which of our 3 possible ways of quantifying that substance do we have info about? Pause the video and see if you can figure that out based on this question. Okay, you should be able to recognize that we're starting out with 3.89 times 10 to the 23rd molecules of propane. Okay, so our known compound or our known substance is propane. Okay, and we have information about the molecules. Okay, formula units, you guys. This is where atoms, particles, molecules, lump them all together, and we call them a formula unit. I don't really like to teach formula unit specifically because kids just abbreviate it FU, and I think they get too much joy from writing that all over their papers that they give me. Okay, so if I say atoms, particles, or molecules, those are all kind of this idea of a unit or a thing, one thing of, in this case, propane. Okay, so we know how many particles or molecules of propane we have, so this is where we're starting at. Okay, and what does the question want us to find? Well, how many particles of carbon dioxide? Okay, so again, we see that word particles. That's kind of a type of a formula unit. Okay, but now it's of carbon dioxide. It's of a different compound. Okay, so we're going from formula units of propane, 1, 2, 3. That's how many steps it's going to take to get to formula units of carbon dioxide. Okay, and let's think ahead. What are the conversion factors we're going to need? Well, look at, we use Avogadro's number twice, right? We'll use it in step 1, again in step 3. In step 2, we're going to need that mole ratio from our balanced equation. Okay, but let's start setting up our T-chart so we can see how all this stuff cancels. Okay, so just like we want to know how many particles of carbon dioxide. So we're going from the top left of our flowchart to the top right of our flowchart. Okay, and we said in that first step, we were going to use Avogadro's number to convert from molecules of propane to moles of propane. So what is that going to look like? Well, just like always, start with what you're given, 3.89 times 10 to the 23rd. And you'll notice I tend to write these smaller just so that my T-charts don't take up, 87 pages worth of lines. Okay, 3.89 times 10 to the 23rd molecules of propane. Okay, and we said we want to convert that to moles. Well, remember the way we're going to convert particles to moles is by using Avogadro's number, right, which is that 1 mole of anything is equal to Avogadro's number, many of that thing, right? So that means 1 mole of propane is equal to 6.022 times 10 to the 23rd molecules of propane, right? And I know that's kind of little. This is the line for my T-chart. Okay, so 1 mole of anything has Avogadro's number of those things, right? So if we look at our unit cancellation right now, right, we had molecules, we divided by molecules, we're left with moles of propane as our current unit. Okay, but of course we don't want moles of propane. We're trying to get all the way to the top right over here. So we need to figure out what's the relationship between moles of propane and moles of, in this case, carbon dioxide. Well, we had that in our previous problem, right? In number 8, we knew that 1 mole of propane gave us 3 moles of carbon dioxide. And where did those numbers come from? Again, those come from our balanced equation. Okay, for every 1 mole of propane we put in, I'm going to put that on the bottom. Again, I put that on the bottom so that my units cancel. 1 mole of propane is going to give us 3 moles of carbon dioxide. Okay, so now we're here. If we stop this problem, we are at moles of carbon dioxide, right? Because we canceled out our moles of propane units. Okay, but we don't want to be at moles of carbon dioxide, right? We want to be at particles of carbon dioxide. Okay, so to go from moles to particles, we need to use Avogadro's number for this idea that 1 mole of anything, in this case, now we're talking carbon dioxide, 1 mole of carbon dioxide, notice moles of CO2 is going to cancel. 1 mole of carbon dioxide contains Avogadro's number, particles of carbon dioxide. Okay, so in this last step, we have canceled out moles of carbon dioxide. Okay, and that's it, right? Our last unit is particles of carbon dioxide, which is what we were looking for. Okay, I'm going to walk through the calculator input on this one because we have a lot of scientific notation going on. Although, look at what we've done. We have Avogadro's number on the top, Avogadro's number on the bottom. Okay, I'll show you both ways to calculate this. You can either leave them both in there, or if you are math savvy, you might notice we're going to divide by Avogadro's number, and then we're going to multiply by Avogadro's number. So really that value is going to cancel out. Okay, but let's work through the whole thing just to see. Okay, so we're starting with 3.89 E23. Notice I'm using that E function, no parentheses or anything, divided by 6.022 E23. Okay, so that's divided by Avogadro's number, times 3, times 6.022 E23. Okay, so this calculation was including Avogadro's number. Okay, when we do that, we get, rounded to 3 sig figs, 1.67 times 10 to the 24th. Okay, make sure you're reading your whole screen. E24 times 10 to the 24th particles of carbon dioxide. Okay, let's do the calculation again, but this time we're not going to input Avogadro's number because it cancels itself out, right? We divided by it and then we multiplied by it again. So really, we think about those values canceling. What we're left with is 3.89 E23 times 3. And we get the same answer here, right? Oh, I'm sorry, that should be 1.17. Can't read my calculator. See, look at that. Show your work, because if this was on your test and then you just misread your calculator like that, you'd get a majority of the points, y'all. People grade with mercy, computers do not. Okay? And so think about this, though. This makes sense, right? If we reacted 1 molecule of propane, we'd get 3 times as many molecules of carbon dioxide. If we reacted this many molecules of propane, we get 3 times as many particles of carbon dioxide. Right? So in that conversion, it's kind of nice. Particles is going to cancel. I'm sorry. Avogadro's number is going to cancel itself out. Okay? So that's it for the examples in your PowerPoint. Okay, in our next video, we're going to work through some of the examples in your stoichiometry practice. So there's a worksheet with, it's 3 pages long, a bunch of practice problems. So we'll take a look at that next. All right, stay tuned.